In this video, you will see me reverse C rubbish from GTA 3. It's going to be in two parts. The first part will be going through this IDA code and making it more readable. And the second part is going to be turning that into actual C++ and putting it into the game. So it's not going to be a tutorial on the basics of IDA, although I will go a little bit about the functionality, but it's mostly going to be my thought process and just you watching me work. So let's get started. We have the functions view on the left, and you can, with Control F, you can type in a little search string on the bottom, and then you will see all of the functions that match that string. So we just put in C rubbish, and we get the 6 functions that that C rubbish has. We also have the mobile version here, which has symbols, and that is very useful. As we can already see, we have a couple of names here that we do not have in the PC IDB. I just haven't copied the names yet. So we're going to use this mobile thing to get the names, but mostly we'll be working on the PC code. So that's the functions. On the right, you have the actual pseudocode. So this is what the Hexrace decompiler does. The traditional IDA view is this assembly view, which has the address where an instruction is loaded in memory when the executable is run. Next to that, we have the stack pointer offset. I don't know if we're gonna get into that, and then you can have the actual machine code displayed, and you can change the settings in the options. So number of opcode bytes, which is 10 in my file. So if you set that to 0, you don't get any machine code. And the stack pointer is the screen number, and so on. So you can go through this and fiddle with the settings. So assuming that you don't have a decompiled view and you're in assembly view, you can just hit F5 to decompile this function and go there. And then you can switch between assembly and pseudocode with tab. Okay, now let's jump into the code. So let's see what we have here. We have this function init, which is called when the game loads, and you can check where a function is called with x, which it's jump to xref, which gives you the cross-reference window. So you can see this is called from cgame initialize. So this happens once per game start. And we have update, which happens on cgame process. So this happens once per frame. And we have render, which actually draws all the rubbish. So rubbish, by the way, is newspapers and leaves on the lying on the ground. So these are the main functions. We also have shutdown, but it's not very interesting. It just frees resources that it got in it. We have stir up, which is quite interesting. This stirs up the rubbish when there is a vehicle going at fast speed. And visibility, which disables it, which disables or enables rendering. So let's start with init, and let's compare with the mobile version, because we have a couple of symbols here. So First of all, we have some simple stuff like rubbish invisible and visibility. So this is a Boolean, and this is an alpha value. And the way I copy names is to put the mouse cursor on that variable, hit N to get the name, just copy that, escape to close the window, and then do the same here but with paste. So that was visible, invisible. So it's this thing, and that way we can copy a few names. And we also see that the game loads a few textures here, which are obviously the rubbish textures. So we have newspapers and leaves. But the textures aren't quite right yet. So let's take a look at mobile, and we see that we have, whoops, we have one texture here that is assigned to the variable, and the others have no name, and that is because rubbish texture is actually an array. So when you look at the addresses, they are 4 bytes apart, and that's obviously an array then. So the way to declare an array in IDA is to go into assembly view just by double clicking the variable and then typing asterisk. This gives you the array window, and then you can tell IDA how many elements your array has, and it will oh no, actually we first have to change the size of that, because right now it assumes it's only 1 byte. So with the D key, we can change the size to 4, which is the size of a pointer on ARM, and then with asterisk we get the array dialog, and it will default to the array size will default to all the free space that is after that variable, so everything that is unused. And obviously these are used by the code. So we manually overwrite this with 4, hit OK. Yes, it will overwrite this. And then when we go back, we see this nice decompilation. So let's take this texture, this name, I mean, and copy it here, and do the same thing in our PC IDB. Okay, so now this is looking a little better now. Let's see what else we got. So, well, this is a bit ugly on mobile. It looks a little better on PC. But essentially, we have a loop of 64 iterations, and it's initializing something here. So this is most likely going to be an array of structs that is initialized in some way. And we see that we have 2 counters. The one counter, v0, is just the actual counter of elements, and then we have a second counter, which is more like it's actually an offset into the array of structs. So when we go to assembly view, we see that this is 4, 4. So this is going to be the size of elements of this array. And if we look, oops, wrong. And if we look on mobile, we see this variable a sheets. So a in the GTA coding style, which is not consistent, but usually an A stands for array. So this is an array of sheets, and sheets we can already tell are probably the actual rubbish sheets, the single rubbish sheets that the game renders. So so the size of a sheet is hex 44 bytes then. And so what we're going to do is create a struct for this. Actually, we have to pick a name for that struct, and it turns out that in the render function, no, not render, in update, we have a function called C1 sheet, add to list and remove from list. So C1 sheet is quite obviously the name of that class or struct. So that's the name we're going to use. And the way I create structs is in the local types window. So when you hit insert, you can probably also do it in the menu. Yes, insert. You get a window, and there you can declare a C or a C++ type struct. So we're going to do that. And let's just leave it maybe empty for now. And again, with Control F, we can look for it. And then when you double click, it's gonna be synced with the with a database. So there's like two different worlds: the decompiled world and the assembly world. When you double click it, these will be synced, and then you get an empty struct here. So when you press D again, it will warn you first, and then create a single byte inside that struct. And then what I like to do is hit asterisk again, and we're gonna put in our size. So hex 44 is 68 in decimal. So this is gonna be the size in bytes, and remove these check marks, and voila, we have our struct. But of course, this is only raw bytes. It's not going to be very useful, but we'll figure it out. So maybe it will be a good idea to start with this with a one sheet function. So we search for them here. We have add to list, remove from list. Okay, this function is actually not used on mobile. It's still there. So add to list. Now this looks like actually let's do this here. Add to list. This looks like it will link this one sheet into a linked list of sheets. So when we see this call, this means that that C1 sheet is a class, and this is a function of this class, which is not static. So the first argument of this call is always the type of the class. So we can, didn't explain this. So to change a type, you hit Y on the variable, and then it will ask you for a type. So it's going to be one sheet and a pointer to that, because this is always a pointer. And I believe the second element is also a C1 sheet. We can tell that from the symbol we have from mobile. So declare that as a one sheet as well. So with n, let's just call it sheet or something. Now we're gonna see a lot of ugly casts here, and that's because we have declared everything as bytes, but well, it's obviously not bytes but pointers. So double click that, and we can then turn with using D, or using D, we can turn that into a 4-byte value, which is the size of a pointer on x86. So this is looking better now. And the same thing with this field. Now this is looking better yet. And we know that this is a pointer probably to, well, we can see we're assigning this, which is of type C1 sheet, to this. So we can tell that this field is of type pointer to sheet. And similarly, since this is a one sheet, we can declare this type to be a pointer. So now this is looking a lot better. And we already have some parts of our struct done. Now let's think about what this is, because it says add to list. So it looks very much like some linked list data structure. So let's take a look. We can check what it's doing on mobile, because we have the arguments here. we have add to list, then the sheet that we want to add to a list, and then we get this name even, start static list. So this is our list, and this is the element that we add to this list. So actually, this is the list, not the sheet. So we take this field and assign it here. So, well, linked lists are always can always be a bit confusing, but let's just call this next and pref for now. It's probably correct. Let's make sure. So we have this element. The next element will be yeah, okay. So what this list node does, it has in its next pointer the beginning of the list, and the previous pointer is probably null. So to insert this at the start of this list, we set the next pointer of our element that we want to add to the beginning of the list, and with the previous element, we're pointing back to the beginning of the list. And then what are we doing here? So, and result, this was the, let's call it old first or something. This was the old first element of the list before we added this. So we have to adjust the pointer here. So the previous element then, yeah, it points back to the new first element, and the return value is probably just bullshit. But yeah, IDA likes to analyze a lot of return values where there are none, so we can just declare this as void, and as a result, the code actually looks a lot nicer now. So we could actually almost copy this directly to C++. Okay, so this adds to a list, and let's take a look at remove from list. This also takes a C1 sheet, and it also doesn't return a thing. Yeah, and we can tell that this is just removing an element from a doubly linked list. So the next prev is assigned prev, and prev next is next. That's a typical remove. Okay, so we have our struct one sheet. So, oh, by the way, with Control E, you get this window. So we can look at it in C style code, which looks a lot nicer. So we have next and prev at the very end. Now let's turn to init. Yeah, so this is still looking quite ugly, but we have already seen a few names in the mobile IDB. So we have start and end of empty list. We have start and end of statics list and start of end of movers list. So we have 3 lists that each have an end, a start and an end. So let's find these in the PC IDB. So because we declared our types in the C1 sheet functions, IDA already analyzed this thing as being of type C1 sheet, which is very nice. So we have one next and prev. So this is most likely to be a C1 sheet as well. So let's go to assembly view, and with Alt Q, you get the type, the struct type window. So with Control F, let's find our one sheet. Yes, and we have one sheet more. So yeah, this makes sense. So we have one sheet pointing to a next element and having a previous one. So this is the start, and we have one pointing to the start, back to the start, and the next one. So this is the end. Let's see if we can find out which one this is. Well, it could be statics or movers, I guess. We can find out, but let's continue some more. So we have already seen uh, stuff like this down here. So this is also a sheet. And by the way, you can hit F5 again in the pseudocode view to refresh it. Um, so we have Previn next here. So this is also a one sheet. And this actually now looks like our array that we saw on mobile. So we copy the name A sheets, rename this. And yeah, it looks like the decompiler doesn't know this type yet, even though the assembly view knows. So with Y, we have to change this type to C1 sheet, and we know it's an array of 64 elements from this loop. But now the assembly view doesn't know yet that it is 64 elements. So let's punch that in. Okay, now this is looking a lot better. And our old this thing that we defined earlier now turns out to be the last element of that array. Same thing. Okay, this is already one sheet, but this also has to be one sheet. All right, so this is looking a lot better now already. And we can start thinking about naming these now. So let's see what we have here. We have the so here we're dealing only with the empty list. So that makes sense because when we initialize everything, we want to add all the sheets that we have to the empty list where we can allocate them from. So if our loop index is at the end, we want to mark we want to have our sheet point to the end of list marker. So end empty list, it's this one, and start empty list is this one. So that makes sense here. Now we still have the statics and movers list. And that's probably gonna become clear when we reverse update. Yeah, I'm actually we have some undeclared here. So actually, just by the order in which this is done, it's probably going to be statics first and then movers, but sometimes these things are rearranged and I wouldn't depend too much on it. I I think we can be pretty sure here. So we start with the start, right? And then we have end here. And then we have start movers and end movers. Yep. All right. So this is looking a lot better. Already starts to make sense. So this is stringing together all the sheets that we have in a linked list and putting it into the empty list. Then we initialize the movers and statics list here, and this, well, we're gonna have to take a look at this. So we have some variables here, rubbish index list and index list 2. And this looks like an array. So all these elements are initialized separately. So these are 6 elements. If I actually, first change the size to a 2-byte value, and then we have 1, 2, 3, 4, 5, 6. Correct. So that's index list 2, and we see that this now is analyzed correctly as an array. So we have 0, 2, 1, 1, 2, 3. Yeah, it's kind of hard to see that from here, but it's going to be pretty obvious. Okay, so by the way, Xref does not work well on other platforms that aren't x86. Of course, it could be that this is really just unused, but let's see. So this would be in render somewhere. Well, actually, maybe it is unused. I don't know. Let's check PC code. So so we have an unnamed variable here. Well, I don't know yet. I guess we will figure this out soon. Let's just take a look at render now and see what's going on here. So it's setting up the texture for what it renders. So this is kind of the type. So we have 4 types of rubbish, and this is directly used as an index into the texture array. So that's interesting. And we know that this is a sheet. And now we can start naming some variables here, because in the end, all that sheets do is get rendered. So all the information we need about how they look, what they need to be rendered, is going to be in here. Now let's start looking at some stuff. So we see that this value is used to calculate a sine and cosine from. So this is most likely a float, which we can see here. So double click on that. And by the way, with Alt-D, you get this nice little window, and you can just directly click on float. So this is a float now. That was F5, by the way. And let's name that angle for now. Because, well, it's an angle, obviously. And field 1C, I believe we have seen in it already. Yes, it was reset to 0 here. And here we check whether it's 0 or not. So it's only rendered, anything is only done with it if it's not 0. So this is like some is used or something, I don't know, active, whatever you want to call it. We can also see that we have a couple of floats. Oops, that we have a couple of floats here again. So this V3, so the camera position X is subtracted from that, and 4, Y is subtracted from that, and 5. Okay, well the vertex Z is set from that, so we can tell that this is X, Y, and Z, and this actually isn't a float then, but a vector. And with Alt Q again, we can find our C vector. Yep. And this is looking nicer already. Oh, we have a second position. So let's declare this type this field C as a vector as well. All right. So this is like I don't know. Let's call this position 1 and this oops and this position 2. I don't know what they are yet, but we will find out. So there's XYZ. We can also call them XYZ just to make it a little clearer for us. And we have field 3,8. Now this looks like, well, I don't know yet. Maybe a Boolean, maybe an alpha value or something. So yeah, so this kind of looks like alpha. Yeah, you can tell here rubbish visibility is multiplied by this value v2. So this is yeah, probably just the alpha value, I would say. And then the result of that multiplication, yeah, this is turned into color here. So this is definitely alpha, and this is also some kind of alpha. Okay, so still don't know what that is. Maybe something like is visible or so. Actually, we see that v6 is used here, and we see those float constants. This is very ugly in the decompilation view, but with y, you just can make that a const, and it will turn it into a nicely readable number. Yeah, maybe this is like a fading state, fading in or fading out or something. So yeah, we can just continue some more. So field 20 is also a double word, and since this is subtracted from the time, we can tell that this is some kind of timer as well. Oops, not timer, timer. And this well, let's just call it timer 2 for now. It's probably some kind of fade in speed or something, whatever. So we have some more float constants, and by the way, my habit is always to check x revs of these floats to check whether they ever written, because if they are ever written, they're not really constant. So these are only read twice in this function, so we can just make that a const, and this is also const, and this is also const, and this is const. Okay, that's looking a lot better now. Okay, so what's happening here is that we are generating the vertices for that for one sheet of rubbish, putting that into the vertex temporary vertex buffer, and rendering that buffer out down here. Now, unfortunately, IDA is very bad at decompiling arrays of structs or arrays of arrays, so multidimensional arrays. So this looks pretty ugly, but actually it's not too bad. So we can tell that these are the vertex x, y, z coordinates, and the texture coordinates, and the color, and so on. So yeah, the color will be the same everywhere. So let's just call that color. And the UV coordinates obviously just going to be 0 and 1. Yeah, so let's take a look at what these are exactly. We've seen them in crubbish init. So this is used. Okay, so this So what we're doing is we're putting 4 vertices into the vertex buffer, and we're putting 6 indices into the index buffer, because with a quad we draw that as 2 triangles, and 2 triangles are 6 vertices. So these indices then reference the vertices in the vertex buffer, and we are rendering that out down here. So this would be the triangle list enum, or define, I don't know. So we're using, okay, so temp buffer indices stored keeps track of how long our temp buffer, our index buffer is, and then we just add six indices, and then we add 6 to that number of stored indices. So that's fine. But we have to take a look at what indices we are adding there. So they seem to start with this. And of course, that's no longer color here. It's redefined. It's quite a bit unfortunate. Yeah, but we see that this is the first element of an array, and this is the second one, and then we have E4, and this should be E4 here, and then we have E6. So this is an array of six 2-byte values. So that makes sense. And these are the indices that define the 2 triangles that we draw. So let's check the xrefs again. Hit F5 to update this. So this is looking a lot better now. We have an array 0, 1, 2, 1, 3, 2. That's exactly um, 2 triangles, and we would expect something like that here. Okay, xrefs don't work, but let's see what we have here. So this would probably be the rubbish index list. So we have xrefs for that. Yeah, so that's all good. Now we still have this thing that we couldn't make sense of on mobile, or rather it looked like it wasn't used. So 0, 2, 1, 1, 2, 3, 0, 2, 1, 2, 3. Yeah, so that's the second array, whether we need it or not. And this was the index list 2. Hit F5. So indeed, this is only used in init, so this is actually unused. Who knows what it was for? And this, what's this? Oh, that's that actually looks. So we can tell that this is a float, by the way, because this is 1.0. So it looks like an array. And we have that same array here. Let's check. Well, I don't know what that is. Could be unused, maybe we just don't know it yet. So let's continue with render. So we figured out our globals, that's fine. We have our angle, we have an alpha value. So maybe let's take a look at what we're doing here with the x and y coordinates. So we have two values. It seems one is derived from the sine, so we get the sine of the angle, and this is just x86 stuff. You can totally ignore that. So this is multiplied by 0.4, and then the angle is used again, the cosine this time, and 0.4 as well. So it looks like all our sheets will be square, and this is like the vector, like a side and like an x and y vector to define um, the four coordinates of the sheet. So yeah, I think we will worry about this when we write the C++ code. So we don't quite know what these are yet, and we have a couple of timers, and that will probably become clear when we look at the update function. So let's do that now, but first let's take another look what we have so far. Okay, so we have some positions, some timers. Okay. Now it starts out pretty simple. So if it's invisible, we reduce the visibility by 5 and clamp it at 0. And if it's visible, we increase it by 5 and clamp it at 255. So that's pretty straightforward. Now we walk the empty list in this first part. Well, actually, we don't walk it. We just check if we can take an element from the empty list. And let's turn that into consts. So we're getting some random value here. And this will be an angle, and the angle is multiplied by some random number and added to the camera position. And the z value is set to the ground value for this position. So actually what this is doing is it takes what this does is it spawns a new sheet around the camera. So let's call this variable maybe spawn angle or something. What I like to do is just call it that as well. Ida will rename it because we can't have the same name twice. So we have the spawn angle, and this is the spawn distance from the center of the, from the camera position. So it spawns it around, in a circle around the camera. And this is the angle, this is sine and cosine. So 18 is the basic distance from the camera that those sheets will spawn, and then we add a little random number to that. And the spawn angle also, it also chooses an angle depending on a random value and the camera orientation and so on. So we get a spawn distance and a spawn angle, and then we set these positions. And this is another const. And it checks if for that position there is a ground z, and when there is one, then we will add this sheet to the statics list. So the statics list is the list of sheets, well, it doesn't move, obviously. So they're just lying there, and every once in a while, and this will be done here, they will be moved around a bit. So this is now in use. Set some random angle. And find attributes for cores. No, actually, let's check what these are. We have them in our project already. So this is attribute zones, which is well, probably in the header. So this is no rain. So the no rain zone will turn off rendering of rubbish, because the idea is that it doesn't rain inside. So when it doesn't rain, it's likely to be inside, and inside you also don't have rubbish. So let's set this to like is visible or something. So no rain zone. So if it's then we turn off visibility. Okay. So that's spawning sheets. Now let's take a look at the moving sheets. So actually, let's maybe start down here, because it looks like this is going to move all the sheets that are already in the moving list, and this is adding sheets to the moving list from the static list. So maybe we will start by adding some sheets, and those consts. Oops. Okay, so what we find here is another position, quite obviously. So let's define, wrong, let's define that as a vector again. And this will be like position 3 now. And this is some z value, it seems, to turn that into a float. Let's call it some z for now. Okay, so how does this work? We take the frame counter, and depending on the wind, there's another constant. Depending on the wind, we get some kind of frequency constant, and if the logical, the bitwise AND of that with the frame counter is 0, then we will add a static. Actually, it's not as used. This is more like state. We will add a static sheet to the moving list. Remove it from the statics list and put it into the moving list. And for that, we will initialize some variables here. So timer, this is actually like the move start time, because this is the current time and this is when we start moving. And the timer 2 is gets longer the more wind there is, and so that looks like the duration, move duration. So the windier it is, the longer the sheet will move. And also, depending on the wind, we set this position 3, and it looks like, since we're adding this to position 1, this is not actually a position but a vector. So Let's call this maybe move direction or something. So we take this and actually that looks wrong. We're adding, yeah, this seems to be off because we're adding y to z. That doesn't, oops, that doesn't make sense. So so this z should be y. But there is no space for to move it around. So maybe it's not really a vector after all, but 3 floats. So let's turn that into a float, make it no, turn that into a float and turn that into a float. And let's call this the y dist, the x dist, and this one, what is this? Well, it's not clear yet, so remove this name. So we have x, y, and this might be the height offset of the movement. So this is some z value. Okay, so we have our starting position. So let's call this start position. So this is where this is the position we initialize when we first spawn this sheet. And to the start position, we add this distance, which depends on the wind. So this is where we want to move, the sum of which is where we want to move. So this is the target actually. So target x, y, and the z. Okay, so we have a hard-coded 3 there. So this sum z is actually the target z of our movement. And if we then take our target x, y, and z and pass that to the attributes function like before, so if there's no rain, so this is the target visibility. Well, let's call it target is visible just so the naming will be somewhat more consistent. So for the state, we have state 0, which is it's not allocated, it's free. State 1 means it's static, and 2 means it's moving. So have we figured out what this is yet? No, we have not, but we will. So then we remove it from the list it was in, which was the static list, and add it to the movers list. So this is how we change state of one of the sheets. Now this will probably take it out of this movers list again. But now we can take a look at these at this this piece of code, which actually moves the sheet. So the current time minus move start is how far we are in to the movement. So like the current time or something. So if that is less than actually, yes. So if the current time is less than the move duration, we still have something to move. Otherwise, actually, this is the piece of code that removes it from the movers list. Otherwise, the animation is done. We reset the state to static. Set our position. Maybe let's call this base position or something. we set our position from our target, remove it from the moving list, and put it into the statics list again. So what we have here then is the animation. Now let's take a look what's going on here. So first of all, we seem to have, a couple of floats. And we have an array here. So is that the same array? So I have, well, I don't know yet. So let's take a look what mobile does. Check update. So where are we? We're probably here. So we see that we have a animations on mobile, which starts out with a lot of zeros, so 102 elements. And this is somehow used for the movement. And since we don't see any other array, it would look like all we have is this animation array. So this is 16. So let's just assume this is our animations array. And that looks good. Rename it. Tell it that this is an array. Well, okay, that doesn't matter. Okay, so what we have now is the array that defines the animation. So this is just a couple of floats. So let's see how this array is indexed. So this looks like some kind of type. So we have 34. Yeah, so we have 3 sets of 34 values. So actually maybe we can, well, that doesn't work. As I told you, Ada is not very smart about this. So it looks like this will be the animation type, which indexes into one of the 34 values, sets of values. And then this will be the element inside that range of values that we're interested in. So strangely, this is this is very complicated. Now what we do see is 17 and 18, and 17 times 2 is of course 34. So it looks like this set of 34 values is again divided into 2 parts. So what we see here is that the position X, so this is like the animated position. We may rename this later, but for now let's call it that, is the base position plus a scaled version of this distance we want to move this. So this could be called like a parameter t. And what we see is that this t, it looks like it interpolates between 2 values of the animations array. So we have v13, which is like, let's call it t1 maybe, and 1 minus t1, which is T2. So this looks like a linear interpolation. And the values in the animation array would then give us how far we are in the animation. So it's not just a straight linear movement, but controlled by this array. So maybe let's find out what T1 is. Let's call this duration, and how this stuff is used. It looks quite complicated. So the X and Y movement looks pretty simple, but the Z movement is not very simple. But essentially, what we're doing here as well is interpolating between two states in the animation. So it's pretty much the same that we're doing here. So let's check. So T1 times this value, and then T2 times this value. So this whole expression is our T for the Z coordinate. And what we call what we multiply T with is the distance we want to travel. So this then must be our Z distance, or Z. I keep switching between Z and Z. Well, okay, so, and we're adding this to a, so this is also some kind of T. Let's call it maybe, well, maybe call it S. So this is interpolating between the position we started with and that we are that we want to reach, and this gets added to this interpolated Z distance. Okay, let's just, yeah, I think that makes sense. So we move from one point to the next point, and then in addition to that, we move a bit, we move up a bit and then down again through the animation. That makes sense. And we're also changing the angle. So while we're moving this thing, it will also rotate a bit. Now, what I find interesting is that I don't see where animation type is set. This could, of course, be in stir up, which we haven't looked at yet. Anyway, so we have a couple of things reversed now, or we understand this now. So this is where we spawn a new sheet. This is where we move a sheet that's being animated. And this is where we end the animation, put it back into the statics list, and this is where we put it into the animation state from the statics list. So let's check what we have here. So this is a loop. So for a number of sheets, oh yeah, it will check. Whoops. It will check. So it will determine the distance from the camera, and if it's greater than well, if the square is greater than 361, which Can't figure out. Oops. So if the distance is more than 19 units, then we put it into the empty list because it's no longer visible. Okay, so that makes a lot of sense as well. So the only thing that's left here is figuring out exactly how this animation array works. And I do remember having trouble with this when I reversed this for Vice City Stories from Vice City. Um, maybe we will do that in a later video. I think this one is long enough already. Um, yeah, we see that there is another animation type here in the stirrup function. And there is a curious thing about the stirrup function because so this symbol, um, as you can tell if you have some experience, uh, is taken from the PS2 version where the automobile is used to stir up. So let's declare that. Where automobile is used to stir up sheets, whereas in the mobile version we have stir up taking a vehicle, and this of course because the PC version and the mobile version of GTA 3 already had some partial support for bikes in them. So an automobile cannot ever be a bike, but a vehicle can be a bike. So it's still only called from the same function, but there's probably some code that we didn't get because it wasn't finished that would have called this from the C bike class or something. And that's probably what it does in Vice City as well. So I don't think we will do this for now. It's a bunch of kind of ugly floating point stuff. So yeah, here we check the state. If it's static, we use the base position, and if it's an animation, then we use the animated position, and we check the visibility. We check the visibility, like we interpolate between the visibility it would seem, right? Well, I don't know. So yeah, that's it for the first part. Thanks a lot.